dynamical tides, and before that, he was a student in CMI. So I will hand it over to Abhishek for the talk. And if you have any questions, I think we can ask at the end because of the online thing, and let Abhishek continue. Yeah, Abhishek, please.
Yeah. Thank you very much for the invitation, and good evening, everyone. So today I'll be talking about modeling dynamical tidal interactions in general relativity. So the work I'm talking about is based on this archive preprint that arrived on the archive maybe a few weeks ago. So yeah, so my work. Oh, okay. Yes, this is good. Yeah, so in today I'll be talking about the physics of neutron star tidal dynamics and their impact on gravitational wave emission from the system. So let me begin by playing a movie of a neutron star binary neutron star event. So in this movie, the two blobs shown here are two neutron stars that are going around each other. There is also some simulated gravitational wave emission from the system shown here. And then the electromagnetic signal, the gamma ray emission after the merger will be shown here. So I'll play this movie and then we can analyze the different stages of the event in the next slides. Yeah, so that was the movie. As you could see, there was a lot of dynamical and very rich dynamical structure in the event. So let's now understand what are the different stages of a binary neutron star event and then proceed from there. So yeah, so in this cartoon, the bottom panel shows the different stages of the binary neutron star evolution. The top panel shows the gravitational wave signal emitted by the system during these stages. So initially, so the movie started in the late stages of the evolution. So initially, what happens is you have two neutron stars shown here as orange blobs that go around each other in quasi-circular orbits. And when they enter the LIGO band, they emit gravitational wave frequency between 10 to 400 hertz. So at this stage of the event, the objects are moving very slowly, and then you can treat their interactions using post-Newtonian gravity. So the objects are moving slowly, the gravitational fields are weak, and moreover, you can ignore the fact that the objects have a finite structure. So you can treat the objects as if they were point particles. So you just need to model their mass monopole moment to understand the dynamics. Now they continuously emit gravitational waves and lose energy to gravitational wave emission, and the signal that is direct in the detector is very regular sinusoidal waves. As the event proceeds and they keep losing energy to gravitational wave radiation, they approach the late inspiral where they are close enough to each other to feel the gravitational field. And what this means is the objects tidally deform due to the gravitational field of the companion. And that's kind of illustrated in this cartoon by showing that their shapes are no longer spherical. In the latent spiral, the gravitational wave frequency is between 400 to 1200 hertz. So this stage, the tidal interactions are important and they're essential if you'd like to understand the equation of state of a neutron star. So the idea is that the size of the tidal deformation in the star depends sensitively on the equation of state. So if you could model this tidal interaction and then understand how the tidal deformations affect the gravitational wave phase, then you can constrain the equation of state using gravitational wave observations. Finally, you have the merger and ring down, which was what was shown in the movie in the previous slide, and these stages of the event are the merger is extremely nonlinear, as you can see from the waves emitted here, and you require tools from numerical relativity to model this stage. And finally, depending on the mass of the then the black hole settles down to a stationary state by emitting quasi-normal modes. And so these are the kind of three characteristic stages. My focus will be today on the modeling the latent spiral of the neutron stars. So, binary neutron stars are rich source for answering a lot of scientific questions. The question relevant to this talk is, of course, the how do you model the tidal deformation and understand the equation of state. We could realize the potential of binary neutron stars because of the event GW 17. So this was the first multi-messenger event detected in both gravitational wave signals by the LIGO collaboration and in the electromagnetic signal by the Fermi collaboration. So now I'll play another movie, but this time it's a real movie. So what you'll see is in the bottom panel, you'll see the gravitational wave strain from the system as observed by the LVK detectors. And then the top panel will show you the gamma ray emission from the system after the merger as observed by the Fermi satellite. Yeah, so the characteristic sort of chirping signal was seen here, and then there was a peak in the gamma ray emission after the merger. So this event was, a historical achievement, and then it allowed us to probe a lot of scientific questions. But the key question, of course, is in the context of this talk is how do you probe the equation of state of a neutron star? So I'll briefly describe the results from the LIGO collaboration here, just to highlight why tidal modeling is important and what's the end scientific goal. Um, so yeah, so in this plot, what's shown here is on the y-axis you have the mass of the two components in the binary neutron star, and then on the x-axis is the radius. So these orange and blue contour plots show the inferred mass and radius of the neutron star. And to do this, you need to model the tidal dynamics. So the mass and radius can be inferred by understanding. You observe the gravitational wave detector. You have modeled the tidal dynamics, so you know how the mass and the radius are imprinted in the tidal dynamics. And then what you do is you infer, use Bayesian analysis to infer what the mass and radius are. And once you infer the mass and radius, this is kind of the truth. So this is from nature, but you have models for your equations of state. So you have WFF1, APR4, SLY, and so on. These equations of state predict a mass and radius curve. And what you do is you calculate the mass and radius curves and then see if the mass and radius constraints pass through the LIGO constraints. In this case, the first four equations of state do pass the constraints, but the last one does not. So in this way, you can rule out or say certain equation state are inconsistent with the data, and then it allows us to
Abhishek?
put yeah, sorry.
So, yeah, so in this kind of plots, this
Mhm.
constraint, how important is the rotation of the neutron star, or is it not at all important?
Well, so at least for this event, there were like two priors. So you had a low spin prior and a high spin prior. So you don't, at least currently, you cannot measure the spin very well. And neutron stars are expected, at least in the early inspiral, to have very small spin.
Okay. So, but
So at least for this event, it was not that sensitive to the prior in the spins, but and astrophysically, it's expected the spins are very small, like 0.05. Chi is like the A by M parameter.
okay. Okay. So
Yeah.
basically, these constraints will not improve even if our spin measurements are better.
It would, I mean, it will improve in another sense, right? It will tell you like what the quadrupole moment is if you could really measure the
Okay.
spin,
Okay.
then that would kind of make this constraints better because there are universal relations between the two and so
And
on.
these different models of equation of state, these are all single component equation of state, right?
Yes, I believe so. So these all of these are single component equations of state. I mean, some of them like APR4 might have even like electron fraction in them, but I'm not too sure.
So if one uses a multi-component equation of state, okay, because one would expect there is a possibility of a strange core.
Mhm.
Think that constraints could completely change or
I mean, at the end of the day, the constraints don't depend on your equation of state model, right? So if your equation of state model pass through the current constraints, then it is consistent.
no, what I mean to say is that I maybe uh, find more models which is consistent to the
Oh yeah,
constraint.
yeah, of course, of course. These are some representative models from their paper. Of course, there are like many others which pass through the constraints. And I think like one with multi-fluids, there are also ones with multi-fluids which pass through the constraints.
Thank you.
Yeah. Yeah, okay. If there are no more questions, let me proceed. Yeah, so that was kind of a very brief introduction to why tidal dynamics is important if you would like to understand neutron star dynamics and understand the equation of state of a neutron star. Um, so yeah, so now the rest of the talk will slowly get a bit more technical, and the outline is as follows. So I'll begin by giving a brief descriptions of tidal dynamics in Newtonian gravity. So just to set the stage and to highlight the kind of tools and techniques that are used in Newtonian gravity. And then what I'll do is I'll compare and contrast those tools and why they don't generalize immediately or naively to general relativity. So I'll discuss some technical problems that are present in general relativity. And then I'll give a brief survey of what are the different approaches that have been recently proposed to tackle the problem of modeling dynamical tides in general relativity. And finally, I'll present my own research from this archive link. It'll mean the basic idea is to show. So I'll get to the question in 1 second. So the basic idea is to show that the Newtonian-like picture holds true in generativity, and then I'll explain what that is, and then I'll present my conclusion. So I think there's a question by Apratim.
Hi. So, since this you started with the summary, so I just wanted to ask you, for you showed the MR plot and not the lambda M plot, and as I'm sure you know that the you get the MR plot by using some sort of a universal relation, right?
Right.
So, which contains some biases. What's your sort of take on this? Like, how do we should we constrain the equation of state from the MR relations, or it's better to just use the lambda M sort of? uh,
I mean, so as you said rightly, so the lambda m is what you get from the measurement. And so the universal relation, so there are like different levels to the analysis. So you can just use the universal relation fits, right? And then that will give you, there'll be, of course, systematic errors because the universal relations are not perfect. One thing you could do is you could add in the errors as, or you can marginalize over the errors in the universal relations. And so I think that will also give you a more robust approach. And I think that's what people do. Like, don't they marginalize over the systematic, so the sort of the error in the fits?
Yeah, they do. Yes. So I just
Yeah.
wanted to check what is your opinion on this? Because I've heard like contrasting views about where to consider the equation state. But
I think using the lambda m is the right approach, but I don't know if that would be significantly different, right? So your prior on lambda is kind of translated into prior on radius in these plots. But so
true.
if you just put a prior on lambda, I think that's what the initial constraints were. I think this is more easier to explain, so I don't have to describe what lambda is. So that's why I presented this.
Okay. Okay. Thanks a lot.
Yeah. So are there any questions? Can I proceed? Okay, I think I can proceed. So
Yeah,
let me
please go ahead, Abhishek.
yeah. So let's go back to the cartoon again, but this time let's understand the different tools that are used to model the system. So in the early inspiral, the distance between the object is very far, and then you can use tools from post-Newtonian theory to understand the dynamics. So I'll briefly describe how the modeling is done in the next slide, but the details are very technical. Um, but anyway, so in the late inspiral, which is of interest in this talk, you have to use post-Newtonian theory, but you have to enhance the post-Newtonian expansion with the tidal dynamics. So that in mathematical terms, that means you have to model the multiple moments of the objects, and you have to understand how the multiple moments impact the equation of motion. And finally, you have the merger and ring down, which is, the merger requires numerical relativity, which is a science on its own. And the ring down is modeled using semi-analytical tools such as black hole perturbation theory. So my focus will be on how do you add the tidal dynamics to post-Newtonian expansions, and then I'll schematically describe how that's done. So So the way I think about the inspiral problem is there is a clean separation of scales, which allows you to use effective field theory or matched asymptotic expansions to understand the problem. So in this cartoon, I have star A, which has a radius RA, and then star B, which has radius RB. They are compact objects, so RA is approximately m, and then they're emitting gravitational waves to be detected here on Earth. So this is not to scale. So there are three distinct zones in the problem. So the near zone, where the dynamics of the interaction between the two objects take place, is the post-Newtonian zone. And the post-Newtonian zone can be again separated into a body zone, where you are looking at physics at the length scales of the order of the radius of the two objects. So that's the finest scale in the problem. So that's denoted here by RAB. Then as you zoom out, what you see is that there's orbital dynamics at the level of length scales of the order of the distance between the two objects. And at this level, of course, you have to model the dynamics of the motion of the two objects. And finally, you have gravitational emission from the system, which has a characteristic wavelength of lambda. And that length scale is modeled using Einstein's quadrupole formula to leading order. So how this approach schematically is done is you first model the dynamics of the two objects using post-Newtonian theory by assuming that the objects have some multipolar structure. And then what you do is you understand how the dynamics at the level of length scales of the order of the distance between the two objects affects the gravitational emission using Einstein quadrupole formula and higher post-Newtonian corrections to the formula. And finally, if you'd actually like to know what the object is, then you have to model the microphysics. So you describe the structure of the object in the body zone, and then you match it to the post-Newtonian zone to get what the multipolar structure of the object is. So this is kind of the three levels of modeling that is done. So my focus today will be on modeling at the level of the length scales of the radius of the object. So what do I mean by that? So early in the inspiral, of course, we are in we are in the rest frame of the object. So the object is at rest right now. And in the early inspiral, the object is
I'm sorry, can I ask you something? Yeah, so when these two objects are moving around each other, the D is probably the separation between the two that you showed in the previous slide.
Yeah.
But then should not be the wavelength proportional to D, because in general the frequency is related to the separation between the two objects which are inspiraling, and then lambda should also be related to D. So why is D much smaller than lambda, and in that case what fixes lambda?
So what I mean schematically by this is, the characteristic radiative effects in the system are, well separated from the conservative dynamics in the system.
Okay, but D should be of the order of lambda, right? I mean, just to be...
Shouldn't there be a separation by V by C?
Okay, I mean, at least in dimensionless units, they are of the same order.
The characteristic velocities.
Because V by C is like of order 0.1 or something.
Yeah. So it's not much smaller. I don't mean like orders of magnitude. Yeah. It's just in a match asymptotic expansion sense. It's like 1 by 10 smaller or something like that.
Okay, thanks.
And the same applies to the radius. In the late inspiral, the objects are not really very far apart. They are like pretty close together. But you can still assume this match asymptotic expansion holds true. But then, of course, the true test of if it holds true is you have to compare it to something like a numerical relativity simulation. So we are in the rest frame of the object, and then the object is in the early inspiral, it's in a very spherically symmetric shape, and then it has radius RA. And then what happens in the late inspiral is the object's shape, of course, deforms from spherical symmetry because of the tidal field of the other companion, which I denote here by EIJ. This is the leading order quadrupole tidal field. And the deformation in shape to leading order can be described by the multipole moment or the quadrupole moment of the star, which is denoted here by IJ. So how do you understand how the multipole moment depends on the external field? Well, you just assume it's linear response theory. So you say that the multipole moment is directly proportional to the external tidal field, and there is some mass per phi scaling for dimensional reasons. And then this function here, k tilde of omega, is called the tidal response function. So that encodes all the microphysical information about the star in it. And omega here is the orbital frequency, or if it's moving in circular orbits, you can just think of this as the Cartesian wave frequency. So the question that I'm interested in today is, how do we calculate k tilde of omega in general relativity? And so let me now briefly motivate what the answer should look like, and then I'll describe how it's done in Newtonian gravity, and then we'll go to GR later. So you can roughly think of the star as a harmonic oscillator, and this is how you begin physics. You just model everything as harmonic oscillators. So you can think of the star as a harmonic oscillator that looks at the imposed tidal field and then starts oscillating with some characteristic frequency omega f. And of course, the imposed frequency might not be actually equal to omega f. So the response function or the transfer function of harmonic oscillator is shown here. So the denominator contains, poles at approximately the location of the fundamental mode. Omega f is the characteristic fundamental mode of the star. There could be some dissipation inside the star, which is denoted here by the purely imaginary contribution. And then finally, the numerator contains a factor called tidal deformability, and omega f is the characteristic mode frequency. So this sort of harmonic oscillator picture is kind of approximately valid. But in the early inspiral, what you can do is you can basically approximate the denominator using a Taylor series approximation. So you can say that omega is not very close to omega f. Then what happens is, the Taylor series expansion gives you first term, which is called lambda here, which is independent of frequency. This is called the tidal deformability or the adiabatic tidal deformability. And the tidal deformability enters the equation of motion at 5 pn order and also the gravitational wave phase at 5 pn order. So pn is post-Newtonian. And then, all the equation of state constraints I presented in the first few slides are because of the modeling of lambda in the gravitational wave phase by these many, famous works now. The second term, the linear in omega piece, denoted here by C, is invariant to time, not invariant to time reversal. So because it's a purely imaginary contribution, so you send omega to minus omega, then it's not symmetric. That enters the equation of motion at 4 pn order. In the black hole case, the dissipation, you can think of the dissipation is because the absorption of the waves by the event horizon. In the neutron star case, you have to add in some sort of dissipative mechanism. So that could be viscosity, some effective viscosity, or some resistivity inside the star. And finally, you have lambda 2, which is the sort of the dynamical contribution that characterizes how the mode frequency affects the tidal response. And that enters the gravitational wave phase at 8 pn order. Naively speaking, this is only true in the early inspiral. And the reason is there could be more resonances that are active as the inspiral proceeds, and then this sort of small frequency approximation might not be valid at those resonances. The small frequency approximation might also not be valid during the late inspiral, where omega can get close to omega f. So the main goal of this talk is how do you calculate k tilde of omega in the late inspiral or in the presence of resonance. So in the late inspiral, the motion is relativistic, and the stars are strongly tidally deformed. So you have to model it within full GR, and then you have to understand the time dependence in the response function. Okay, so let's now briefly understand how the modeling is done in Newtonian gravity. So just to understand the different tools that are used. So let me briefly present the equation of motion. The details are not that important. So you have the mass conservation or the continuity equation. So d here is the material derivative, rho is the density, theta is the divergence of the fluid velocity. And then you have the Euler equation that tells you how the local acceleration, the first term here, depends on the pressure gradients P here is the pressure, and the gravitational gradient. So U here is the gravitational potential inside the star. And then finally, for the gravity sector, you have the Poisson equation that just tells you how U depends on rho. So this kind of gives you a set of equations to solve in Newtonian gravity. Once you give an equation of state and some boundary condition, which is the tidal boundary condition in this case, you can solve these equations to completely describe the system. So one point I would like to highlight is how do you describe the tidal field in Newtonian gravity? And then we will come back to this because this will be a very important point. So right now there is no tidal description here, right? So U here is just the total gravitational potential. So what you do in Newtonian gravity is you split the contribution into a self field of the star because of its density and pressure and so on, and a tidal contribution, which is a small perturbation because of the separation of the distance between the objects is pretty far. The self field is sourced by the density inside the star, so it satisfies the Poisson equation. And the tidal field, on the other hand, is sourced by the other object. So this is satisfies the Laplace equations, and the Laplace equations can be solved analytically. So the tidal field is given by a spherical harmonic decomposition. YLM are the spherical harmonics. DLM is the tidal moment of the star of the source, and then RL is the characteristic scaling of these spatial dependence. Outside the star, you can also solve for the self field of the star, and the solution is of course given in terms of the multipole moments denoted here by ILM, and the solution decays as R power L plus 1 for the individual spherical modes. And anyway, so this split in Newtonian gravity is nice because what happens is you can view the problem as a force problem. So you have the acceleration inside the star, the local acceleration, it is forced by the pressure gradients, and it's forced by the self potential of the star and the tidal potential due to the external companion. Then this split is very nice. So naturally what you do is you begin by setting the tidal field to 0, and then you understand the structure of the star. So you understand its mass and radius and so on. And then you do linear perturbation theory. And the linear perturbation theory is done or can be done many different ways, but the very nice elegant formalism to do it is used to use Lagrangian perturbation theory. So what you do is you track the fluid elements, and then you use a displacement vector to track their motion. And at the end of the day, the linearized equations can be organized into sort of the schematic equation shown here. So Aij are some operators, Bij are some operators that depend on the density, pressure, and gravitational potential inside the star. Cj shown here is the Lagrangian displacement vector, and Fi is the external tidal force. So it's kind of a force PDE. And physically, what these components mean are Aij is the kinetic energy of the fluid inside the star. Bij is the potential energy. So it can potential involves both pressure and gravitational contributions. And finally, Fi is the external tidal force. So you have these clean separation, and the canonical way to solve this problem is you first look at the homogeneous problem. So you set the force to 0, and then you try to understand what do the homogeneous solutions look like. And you begin by taking a Fourier transform. So you move from the time domain to the Fourier domain. Omega is the frequency. And if you look at this problem, it is an eigenvalue problem for omega squared, right? So you have some operator here, some operator for the potential, and then they are with the boundary conditions that everything is regular at this edge of the star. It gives a characteristic eigenvalue for omega squared. The nice thing about the operators is that they are symmetric. So given any two displacement vectors, they don't have to satisfy the equation of motion. These operators are symmetric. And what that means is, kind of from quantum mechanics, the eigenvalue problem, so the eigenvalue is the eigenvalue of a Hermitian operator. So you can get real eigenvalues. So omega squared is real. And the eigenfunctions, so Cj homogeneous, are a complete set of basis functions to expand any solutions on. So I should say this is sort of a physicist proof because for a mathematician you have to do a lot more work than this. But I'm happy with this sort of proof. But anyway, the end result is that the eigenfunctions are a complete basis and the eigenvalues are real. Okay, so the next natural step to do is, of course, you look at the first problem and then you expand the displacement vector there in terms of modes. So alpha here denotes all the eigenfunctions of the homogeneous problem. It's a label to denote that. A alpha is the mode amplitudes, e raised to I omega t is the Fourier transform, and then C alpha I are the mode eigenfunctions. The mode eigenfunctions are all orthogonal to each other, so you can expand the displacement vector, substitute that in this equation, and then take the inner product to sort of simplify this to the individual mode contributions for the amplitudes, and the simplification kind of results in this model. So it is indeed, that the mode amplitudes are indeed transfer functions of a harmonic oscillator, but it's just not one harmonic oscillator. It can have all the modes of the star. And the main essential point here is the end result of all these sort of computations is the tidal perturbation can be viewed as a first harmonic oscillator problem. And because of, it's a linear perturbation theory, so all the response functions are proportional to the amplitude, and then in the end you can organize it into this sort of sum over harmonic oscillator response functions. And so this completes my description in Newtonian gravity. So next I will sort of contrast it with the GR description. So I'll stop here to see if there are any questions. Okay, so I can proceed. Okay, so now let's kind of contrast the Newtonian picture with the relativistic picture. So the first thing that I emphasized was there was a separation of the self field from the tidal field of the star inside the star. That is not unique inside the star in generativity. The reason is quite simple. So if you look at the Newtonian equations, it's Laplacian on U is plus some 4 pi rho is equal to 0. The Laplacian is the same inside or outside the star. It doesn't depend on the fact that there is a star. That is not true in generativity. So the star has its own curvature source, so it couples to the space-time, and the equations inside the star are not the same as the equation outside the star. So you can have a split between the tidal field and the self field outside the star, but inside the star there is no unique split. You can have any split and then that works. So there is no unique separation, so it's not immediately clear what you have to choose. The second point is the tidal field is not dynamical. So what do I mean by that is this tidal field satisfies an elliptic equation. So the Laplace equation doesn't have a time derivative operator there. So all the time dependence is kind of immediate. But that's not true in GR. You satisfy wave equations in GR, so you will have time dependence in the operators. So the tidal field is dynamical.
So something I don't understand. So Abhishek, so if I know the inside matrix, that of the star, okay, then there is a unique split, right?
There is only one solution inside the star, and then there's a boundary condition outside the star. There is no split, right? There is gravitational. There's just continuity between the potentials. There is no split saying this has to be your potential, and then this has to be your
I put
tidal
a
field.
regularity condition at the center.
Sorry.
What if a regularity condition arises at the center or something that cannot fix the split?
It will not. So maybe in 10 minutes I will describe why the split is not unique. Yeah. Yeah. So in Newtonian gravity, there's also a complete eigenfunction spectrum, as I just demonstrated. In GR, that's not true with the traditional modes because you kind of the usual modes that you look at are radiative eigenmodes of an isolated star. So they lose energy to gravitational emission, and they are quasi-normal mode in nature, and then they also have tails and so on. So they do not form a complete set. And finally, there's a nice first harmonic oscillator picture, but that's not it's not immediately clear how to do that in generativity. So I'll kind of try to answer these questions in the next few slides and show that you can answer all these questions if you sort of modify the relativistic treatment that is usually done. So before I describe my results, let me just give a brief overview of the sort of the techniques that have been used recently to tackle this problem. So in the beginning, sort of there were effective one-body models or phenomenological models which used the dynamical tidal response function from Newtonian gravity, generalized it to GR, and then calibrated them with numerical simulations to make them robust. And these were the first models. They were very effective, and they were kind of the first important modeling of dynamical tides in general relativity. More recently, Eric Poisson started the sort of sequence of papers where he systematically tackled the dynamical tidal problem in general relativity. And he wrote some papers in 2020 where he described how to do the matched asymptotic expansions. And then I slowly got interested in the problem. And then more recently with a student, he has, they have obtained the tidal response in the low frequency approximation. So the Taylor series approximation I just described in the beginning of the talk. And more now they've also added nonlinear tidal contributions due to curvature corrections in GR as well. So these are kind of the pioneering works which have used matched asymptotic expansions. So last year we also published a paper which is kind of an improvement on Eric Poisson and his students' work. So we used the low frequency approximation, but we resummed the approximation. So I can explain what we did more later, but at the end of the day, what we could do is we could capture the tidal resonances because of the mode resonances numerically, purely numerically. So we didn't have an analytical description, but we could capture it semi-analytically. And finally, today, what I'll be talking about is the mode decomposition approach. So I'll demonstrate that the Newtonian picture holds true in GR as well. And finally, there are also other approaches which are based on scattering amplitudes and so on. So there are people who are working on understanding tidal dissipation using scattering approach, and also dynamical tides more recently using scattering approach. So these are kind of all the different techniques that are being used currently. So it's a very active field with a lot of different tools. So now I'll start to talk about my work. And so let's go to understand how the mode decomposition approach works. Okay, so let me just flash what are the main ideas in the project. So, before I go into technical details. So as I said, it's important to use Lagrangian perturbation theory because you have all this nice structure, and the Lagrangian perturbation theory for rotating fluids in full general relativity was described by Friedman and Schutz. So I'll be using their formalism. And then what I'll do is, as I described schematically in the earlier slides, the problem is in the body frame or in the local rest frame of the object is part of a larger problem where there is motion at the orbital level and then gravitational emission at the wave zone level. So this separation kind of gives you a matched asymptotic expansion. So you have to match the body zone description to the post-Newtonian metric in the buffer zone. And then this matching is kind of essential, and I will show you what happens when you do the matching. And finally, you need to obtain the tidal response function, and then I'll show you that there is a trick you can use where you can integrate the Hamiltonian constraints of the theory to obtain the tidal response function. So this is kind of the main ideas in the paper, and then I'll briefly describe now each of the important aspects. Okay, so formulation of the perturbation problem. So Friedman and Schutz kind of formulated everything. So I didn't, and they have the summary in their nice book. So I didn't have to, I just had to learn that approach. So yes, so schematically, the equations you're solving are the Einstein equations and the stress energy conservation equations. So you have the tidal perturbation. So you decompose the metric into the background metric plus this perturbation. So the background metric is the TOV solutions, the Tolman-Oppenheimer-Volkoff solutions. You linearize the Einstein and stress energy conservation equations, and then you have to solve the linearized equations. There are a lot of techniques to solve them, but the approach by Friedman and Schutz is kind of very transparent. So the essential idea is the linearized equation of motion can be derived from a Lagrangian or a variational principle. And the variational principle can be summarized in this short sort of theorem. So consider any two abstract vectors. So what I mean by abstract vector y and y hat here is they are just vectors where you have both the displacement c mu. So this is the four-dimensional Lagrangian displacement, and the metric perturbation h mu nu. The same for y hat. For any two displacement vectors, arbitrary vectors like this, we have the following relationship. So I'll briefly describe what each of the terms are. So the first term here, C hat B, is contracted with EB. EB is here is the linearized test energy conservation equation acting on the vector Y. The linearized Einstein field equation is denoted by E alpha beta, and then it is contracted with H hat A alpha beta. And then the Lagrangian for the system is shown here. So L here is the Lagrangian. And then you have a boundary term. So the Lagrangian is a symmetric operator between Y hat and Y. And you have the left-hand side as well. For solutions to the equation of motion, so you can set E beta and E alpha beta to 0. The Lagrangian satisfies kind of this relationship. So you have Lagrangian plus a boundary term is equal to 0. So this operator equation will be essential in our approach. But let me just say that this approach is also related to more advanced approaches like you can have pre-symplectic form, you have a current, and then you can do all sorts of nice things even in gravity and modified gravity and so on. So there's work by Wald and others. So this is connected to the same approach, but I will not be talking in any more detail about those approaches. So you have this operator equation for the Lagrangian. And so the natural step now is to do a 3+1 decomposition of that equation. And then to do that, what we did was we looked at the background space-time, and then you look at the 3+1 split. We assume that the shift vector is 0. So the 3+1 decomposition has lapse vector. So n here is the lapse, and then gamma ij is the spatial metric. So for solutions to the equations of motion, the Lagrangian identity is true, and then you can just decompose that in 3+1 split to get this schematic expression. So the first term here, so y hat A and yb are contracted with an operator O0. And then the same here with the operator O1, and then you also have a boundary term. Well, the operators have the nice property is that they're symmetric operators. So in fact, in metric, this term is symmetric. So if the boundary term is symmetric, then the mass of object 1, the tidal source is separated by some distance L source. And then inside the dynamics of close to the object, the solutions can be separated into sort of 3 zones. The first zone, called the inner body zone, contains all the fluid dynamical nature of the star. And then this zone is, of course, strongly gravitating. The outer body zone is vacuum dynamics, but it is also strongly gravitating. So you have 2 strongly gravitating regions. And then these zones kind of move into a weakly gravitating region in the buffer zone. So D here is the sort of the mean radius of the buffer zone. And in the buffer zone, the post-Newtonian expansion is valid. So what this tells you is, okay, the boundary conditions have to be the post-Newtonian solution in the buffer zone. If you use that solution, you have some hope of getting a symmetric boundary condition. And the post-Newtonian metric, the conservative dynamics does not have dissipation in it. So the dissipation enters at 2.5 pn and higher. So you can worry about dissipation, or you can add radiation reaction on top of the conservative dynamics of the system.
So, Abhishek, existence of buffer zone, is it guaranteed that such zone will always exist and you will be able to match solutions?
At least in the early parts of the late inspiral, yes.
Early part of the late inspiral, yes, when you think the non-linearities are manageable.
Yes, exactly.
Okay.
I mean, that's the same reason post-Newtonian expansions work, right?
Okay. So you are saying as long as the post-Newtonian expansion, so this probably is related to the radius of convergence of the post-Newtonian expansion.
Yeah, that's right. Yeah. As long as you have a valid post-Newtonian expansion, you will have this sort of separation.
Okay.
I think, Abhishek, another way to understand this probably is this inverse of omega that sort of gives you the length scale within which this approximation is valid. So when you go to the merger regime, then your omega becomes high, so this approximation cannot be done.
Yeah, that's correct. So what we did was we imposed the boundary conditions in the sort of the mean radius of the buffer zone. And what you get after that is you get a symmetric operator equation. So for technical reasons, you have to work in harmonic gauge because post-Newtonian theory is done in harmonic gauge. If you could do post-Newtonian theory in another gauge, you should use that gauge because, as I said, the problem is part of the whole system. So you have orbital dynamics, you have bodies on orbital dynamics and gravitational emission. So, and historically, the post-Newtonian expansion is developed in the harmonic gauge. So we had to work in the harmonic gauge. But anyway, you can show the same in the Wheeler gauge. It's not important. So you look at the Lagrangian identity I described before. You look at that in the time domain. You take the Fourier transform. So you go to the frequency domain. These operators are symmetric. You integrate this over a spatial hypersurface extending from the center of the star to the edge of the buffer zone, and then you can integrate this boundary term by parts. And the end result is shown here. So you have the eigenvalue omega squared. This operator here is symmetric. The potential energy operator is symmetric. The boundary term evaluates to a symmetric operator as well. So ILM or I tilde LM here is the Fourier transform of the multipole moment of solution Y. And I hat LM is the Fourier transform of the multipole moment of Y hat. So you see that this is symmetric. So it's just a product. And then you have the mass of the star entering the boundary term. The D here is the mean radius of the buffer zone. And C here is the speed of light. So this is just included here to show that the post-Newtonian nature of the metric in the buffer zone. So up to this order, you see that the solutions or the eigenfunctions will be a complete set. And they are in the spectrum of Hermitian operator for post-Newtonian boundary conditions. So this is kind of one of the key results of the paper. So if you use a matched asymptotic expansion, then you get a complete set of eigenfunctions. Okay, so this is one result. The second result, which is, of course, how do you split the tidal field and how do you extend the tidal field inside the star? As I described before, you cannot do it uniquely in GR, and then the next slide I'll explain why. But outside the star, you can do it uniquely. And then here I show the TT component of the metric in the buffer zone, basically. And then, so I'll get to the question in 1 second. You have the multipole moment here, and then that scales as r per L plus 1. So that's the Newtonian contribution. You have post-Newtonian corrections as well. And then you have the tidal moment, which again has the same sort of characteristic Newtonian plus post-Newtonian correction. So the question is, how do you extend the tidal field inside the star? So there's a question, so I can take the question now.
Yeah, my question was regarding the last slide. So when you have this symmetric boundary condition, you only take the symmetric part of the boundary condition. If I'm not misunderstanding, so the resonance features will not be present here. Is that so?
No, the resonance is present, right? So the resonance has to do with the inner bodies on dynamics. But the dynamics at the orbital level is post-Newtonian. The dynamics in the object zone is strongly gravitating. It's full gravity.
What I mean is, like, in resonance, that actually these comes like 1 by omega square minus omega n squared, let's say, where omega n is these QNMs. But if you are in here, it seems like in a certain way we are ignoring these QNM contribution at the far infinity, and that's how these boundary conditions are becoming symmetric. So in that context, I was thinking.
Well, so that's the point. The frequencies are not quasi-normal here. This is only the conservative part. So there is a resonance.
Okay. And the real part of the frequency is contributing.
Yeah,
okay, got
exactly,
it. Okay, that
exactly.
makes sense. Okay.
The dissipation does not contribute because it will contribute, but it will contribute at the wave zone dynamics level. So you have to add in radiation reaction.
So the frequencies will have a real plus imaginary part. So here only the real part will contribute. It is like
here
Tanya's.
he will be exactly real. They will not have any imaginary part.
Exactly real. So it is like Tanya's omega square minus omega n square, that kind of stuff.
Yeah, exactly. But
okay, got it.
Here you can actually show that that is true. You don't have to assume that's true.
Got it. Okay.
Yeah, so I'll get back to this slide. So I think I have a few more minutes. So yeah, the question is, how do you extend the tidal field inside the star? Well, so let's get back to the problem, right? So let's go to the metric field inside the star. So the bold symbol h mu nu denotes the metric inside the star. So let's just split it into some contribution for the multipolar or the self field of the object and some tidal contribution denoted by ht. You substitute that in the linearized metric equation, sorry, the tensorial equations and the stress energy equations. The split kind of gives you these equations. So you have E mu nu plus the self contribution plus the split due to the tidal contribution. The same for the stress energy conservation equations. Now, as you can kind of see, like you cannot just set this to 0 because it is coupled to the stress energy conservation equation. So you cannot get a unique solution in that manner. So any split that kind of works like this is an actual valid split inside the star. In Newtonian gravity, it just happens that there is no coupling between the fluid motion and the tidal field, and the operators inside and outside the star are symmetric. To use the complete set of modes that we used in the, presented in the last slide, some constraints have to be satisfied. First, you have to satisfy the linearized Hamiltonian momentum constraints in the theory. And then you also have to match the right boundary conditions. The self field of the star has to match to the multipolar boundary conditions in the buffer zone, and the tidal field has to satisfy the tidal boundary conditions. And any decomposition that satisfies these two equations works. Like you don't have to impose any additional constraints. So you could have an infinite set of fields that satisfy these two constraints, and they work. They are a valid split inside the star. This is in fact even true in Newtonian gravity. You don't have to use the tidal field that is usually used. Like you don't have to set r power l inside the star. You can just set r power l plus r power l minus 2. But what that will do is that will introduce another additional sort of gauge dependent force in your problem. But that's okay. Like that's in Newtonian gravity, there's a preferred split, but there is no preferred split in general relativity. You can have any split, and then that's completely valid. So yeah, we will demand these two conditions, and what do they mean? So you have to set this sort of contribution. The t here is the time component, so all the time components of the constraints have to be satisfied, and then the tidal part of the metric perturbation has to consistently match to the tidal field exterior to the star. And then if you use this as your restriction, then the field equations for the self field are the Hamiltonian momentum constraints of the theory. So this is true. You also have the evolution equations for the metric self field of the star, but now it's sourced by some tidal stress tensor, and the tidal stress tensor is shown here. There could be some choices of the tidal stress tensor which could set this to 0. I do not think that will be consistently possible because the Bianchi identities won't be satisfied. But anyway, any field which satisfies this condition will source in some non-trivial way a tidal stress tensor. And then the fluid part, of course, gets a tidal force, and the force is shown here. So these two objects, the tidal stress and the tidal force, are not unique because the split is not unique. And the self field, of course, because of this consistency condition, matches asymptotically to the post-Newtonian boundary condition, and then you can use the mode solutions that we described in the last few slides. At the end of all this, what you do is you go back to the 3+1 split of the Lagrangian identity, but you now have a force on the right-hand side, which depends on the force and the tidal stress tensor. And then you decompose the solution in terms of modes, take the inner product, repeat the same things you did in Newtonian gravity, and the result in the end is the amplitudes, the mode amplitudes AS satisfy an effective harmonic oscillator equation. Fs here is a relativistic force, so it has all these contributions, and it's quite a complicated expression. But in the end, with the modes, with the conservative dynamical or the post-Newtonian boundary conditions, the modes are complete and they satisfy harmonic oscillator equations. Okay, so now let me briefly describe how you get the tidal response from this. So in Newtonian gravity, the multiple moments are just defined in terms of integrals in the source, but that's not true in GR because it's a nonlinear theory. You don't have such simple definitions. So the multiple response, of course, is given in terms of the tidal response and the external tidal moments. So in how would you do the calculation in Newtonian gravity? So you would look at the Poisson equations in the linearized theory for the self field and the vacuum equations for the tidal field. You get the conserved current, or so this is not exactly the conserved current, it's just sort of a trick. So you multiply this equation by U tidal and then this equation by U, and then you subtract them. So you get something on the right hand side. And then you integrate this over the surface of the star, and then the first term here is shown on the left hand side here. And this term can be integrated by parts to obtain an integral over the surface of the star. And at the surface of the star, you know what the boundary conditions are. And then they are precisely that the tidal field scales as r power L and the multipolar field decays as r power L plus 1. And then you substitute them, and at the end of the day, this surface term evaluates to the tidal response function multiplied by the tidal moment squared schematically. And then you can expand the left-hand side here in modes. And what happens is in the end result is a sum of harmonic oscillator response functions. And then this was what you would get in Newtonian gravity. But this also gives you the motivation of what to do in GR. So you look at the Hamiltonian constraints. So you look at the Hamiltonian constraints for the tidal field and the self field. You multiply them by the TT components of each of the metric trace reverse metrics. And anyway, the result in the end is some schematic operator like shown here, a love plus a boundary term, which is denoted love because the tidal response function is also called the love number sometimes. And then you integrate these constraints throughout the star as in Newtonian gravity. And then what you get is the end result is the same sort of expression. So you have the tidal response function as a mode sum. And IS and GS here are relativistic generalizations of the overlap integrals in Newtonian gravity. You also get a correction factor Q, which is time dependent or frequency dependent because the tidal field is frequency dependent in GR. And in the Newtonian limit, of course, Q is 1 plus some post-Newtonian contribution. And IS and GS are equal in the Newtonian limit, but in GR, they're not equal. They're sort of separate contributions, and they're quite complicated. So yeah, so this kind of is the end point of my talk. So what I've demonstrated is that you can have robust and accurate models of tidal response in full generativity, and they're now being developed. If you use matched asymptotic expansions, you can generalize the Newtonian mode sum approach to a tidal overlap in generativity without any approximations or assumptions. And finally, you have some future directions. So you can use this approach to understand dynamics of resonant excitation and resonant energy dissipation. You can use the same to understand nonlinear tidal dynamics using a mode sum approach. You can extend it to slowly rotating stars, and then you can also extend it to fluids which have an elastic degree of freedom or some electromagnetic field like a magnetar. But you could also have a boson star or other things. You can do the same for all those things. There's also another future work, which is the black hole tidal response, and I've highlighted that in red because the techniques I've used do not necessarily generalize to the black hole tidal response case because the separation of scales do not work. And then I can talk more about this later. So I'll stop here.
Okay, so let us thank Abhishek for this very nice talk. So it is now time for some questions. So maybe if there are some questions from the audience.
Hello.
Yeah,
Yes.
hi.
So in your can you go back to slide 10?
Slide 10, yes.
So why you have used this harmonic oscillator analogy for k tilde omega a priori?
Well, I mean, I kind of know the answer in the end, right?
Yes, you have shown, but a priori you have used this harmonic oscillator analogy. So what was the physical motivation for writing this in this form?
Well, so there are two physical motivations. So one is if you look at a star of constant density, you can show that there's only one mode, and then that is the F mode. And this is true in that case.
Okay.
Right. And then that's kind of the analogy, but you also kind of know the answer in Newtonian gravity, then you can motivate this with the harmonic oscillator analogy. And then, of course, once you know the answer, you motivate it and then show the answer
Okay.
is kind
Okay. Okay.
Any other questions from the audience? Anything else? Okay, so Sudipta, you want to ask anything?
No, I think I have asked question.
Okay, so Vishak, I have two questions. Maybe we can just go over. If you can go to slide 24 and 25. Yeah, I'm sorry, you have to go
okay,
along here and there.
can I go escape? Yeah. 24 and yeah.
Yep. So my question is, you have this two condition that you impose, that is the Hamiltonian momentum constraint has to be satisfied and it has to match consistently with the tidal field. I understand that these are motivated I mean, this has to be satisfied in some sense. But if I use some other condition, for example, regularity at the center of the star and things like that, then also do you think we get the same tidal love number?
Well, so
In other words, your result, how much depends on these assumptions?
well, so I mean, so you need to satisfy these assumptions if you want to use the modes that were, were proved here, right? These modes are described with the multiple boundary conditions, right?
Mm-hmm.
So your tidal field has to be somehow subtracted from your solution inside the star. And that means that the tidal field has to match to the tidal boundary conditions. And the other requirement, which is a technical requirement, is that this operator equation, which I have written down here, is only valid for the solution that satisfy the linearized Hamiltonian momentum constraints.
Mm-hmm.
So because of these technical requirements, you kind of need to satisfy these two requirements to use the modes. Of course, you don't, if you don't care about modes, you don't even have to split the solution in this way. You can just numerically integrate it, and that's what we kind of did in our previous paper. You don't have to split anything. You can just integrate the solution inside the star numerically, match it to the external solution, and then you will get the mode resonances. But you just don't know what the resonances are, right? You kind of see and then say this is the F mode resonance. You kind of see the resonance, say this is the G mode resonance, and so on.
Okay. And in 27, right?
Mm-hmm.
Yep. So here you sort of, where am I? Yes, so you say that surface term evaluates to this KLM by arguing that tidal field goes as R to the L while U goes as R to the minus L minus 1. But my point is, in general, the tidal field is not just a single term. It will have several other subleading terms as well. And in principle, that subleading term can also have 1 by R to the minus L minus 1, which is the known ambiguity in defining the tidal love numbers. And do you think that is going to affect the KLM that you define here?
So this is in Newtonian gravity, right? So here it has to go
Yeah.
as R
But I'm
plus
saying
1.
when you go to the
Yeah.
general relativity, then
That's exactly the point. So that's why I did not want to touch the black hole case, right? So those ambiguities, so R power, I mean, the ambiguity is not in the subleading terms. The ambiguity is at 5 pn, where you can have R power L, so L, and then that can get multiplied by 1 by R power 2L plus 1.
yeah,
That
that's
can
what I
give
was saying. Huh.
exact contribution. So in the fluid case, there's a separation of scales, another separation of scales, which is that the dominant contribution to the response is the fluid dynamical response.
Okay.
So you can ignore that 5 pn contribution as an error in your approximation. But in the black hole case, there is no fluid. So you have to consistently account for that. And one way you could resolve it, and then this is kind of what I feel has to be done in the black hole case, is of course the split between the tidal field and the multipole field has this ambiguity. But the equation of motion for the black hole will not have this ambiguity. Any split you obtain will lead to the same equation of motion.
Mm-hmm.
So I think this is the point Eric Poisson tried to make in his papers. It's that you have to obtain the equation of motion or the gravitational waveform using some gauge invariant approach to show what the response function is for a black hole. In the neutron star case, you can use both Newtonian sort of methods because there's a sort of a separation of scales in the fluid excitation and the gravitational wave or the gravitational dynamics of the system.
Okay, thanks, Abhishek. I think Kobir has a question, and with that, we will end. Kobir?
Yeah.
Yeah, hi. Thanks for the talk. Very nice talk. So I just had one small question. You mentioned in one of your slides towards the end that that generalizing towards a rotating solution would be one of your targets. So I was just interested to know if there was if there are constructions on interior solutions for the full Hartle-Thorne metric. Thank you.
So the Hartle-Thorne metric, so right now, I think people have extended to fourth order. Oh, no, there was a recent paper from my group which has gone to some ridiculous eighth order or something like that. In what I mean in the slowly rotating approximation. So I think there are, the slowly rotating expansion is kind of now done to a very high order, even for neutron stars. Is that the question? I was not sure.
Well, I wanted to ask what is the interior solution, the Hartle-Thorne in the
Yeah. So yeah, the slowly rotating stars, yeah, of course, you assume it's a slow Hartle-Thorne metric, yes.
Okay, thanks.
Yeah.
Thanks, Abhishek, for this very nice seminar, which was illuminating. I hope when you come to India, there will be chance to interact personally as well. So, so I think with that, we say goodbye to you and also to all the participants.
Thank you, Abhishek.
Thank you.
Okay.
See you.
Thanks and bye.